Hello everyone. If you can hear me, say yes. Great. So we have 55 people, which is great. Okay, good. So can you see the presentation? Affine Transformations. Can you see my screen? Perfect. Okay, and we are recording. So learning goal for today, we have only one learning goal, which is affine transformations, but it's kind of a single topic. We will review a lot of things and we have a lot of content today. So hopefully we can cover everything and it will be very nice. Okay, so we were talking about linear transformations on our past lecture. Only one learning goal means, yeah, maybe. Okay, and again, remember, I will not pay too much attention to the chat. Also, neither the TAs, right? So we'll have questions, raising hand, and I will have a couple of pauses for that. Okay, so we were talking about coordinate frames, right? And transformation matrices and linear transformations. So what we were talking about the last time is something like this. So we have a coordinate frame, let's call it E, and let's say that this is our original coordinate frame, right? And basically what we have is this coordinate frame is expressed as a transformation matrix that is composed by column vectors that represent each of the basis vectors of this coordinate frame, right? And right now we are talking about already 3D. I will keep talking about 3D. So we have these basis vectors here, X, Y, and Z, or J, I, J, K, or whatever name you want to put. But from now on, I will use like a 2D version of this, but this is only for visualization purposes. So this blue point right here is basically the representation of this like Z axis that is coming out from the monitor, right? But I will keep talking about matrices in 3D. Okay. So again, this is kind of like the original coordinate frame, like our work coordinate frame, that it doesn't have any distortion or anything weird, okay? And we were talking about linear transformation. So we talk about reflection. This is an example of a reflection. We are basically changing the direction of the bunny. Now it's like seen to the other side by this number here, right? We are just changing the sign of one of these one of the components of, in this case, this basis vector, and this is what we get, right? And we have other transformations like uniform scale, right? In this case, we are scaling the basis vectors 2 times, make them bigger, and again, because this is a coordinate frame expressed as a transformation matrix, it's basically taking its world and distort it, right? And in this case, is scaling its world with everything that is inside the world. We can have non-uniform scales like this one, in which the basis vectors x and z are basically the same, but the y basis vector or the j basis vector is basically scaled 2 times, right? And we also talk about rotations, right? And we already saw what is the actual origin from rotation, what is the actual origin from these weird trigonometric functions. Why are exactly those? So basically, we said this is similar to have a point that is basically traveling along a unitary circle, and its x and y components will be basically cosine theta and sine theta, okay? And I have a quick example here, so I can. My computer is kind of running slow today, I don't know why. Sorry. Yeah, so this guy is now, okay, the animation is horrible because it's very slow and we cannot see like a smooth animation. I will move it manually, right? But yeah, so here we can see, right, the x component and y components are basically these trigonometric functions, and this is because that is exactly the meaning of these trigonometric functions, right? Cosine is the x component of something that is basically traveling around a unitary circle, and the sine of the angle is basically the y component of something that is traveling around a unitary circle. Okay, so that is hopefully good already. So let's talk about another transformation called shear. So this one is a bit different. So it again is distorting the world and is distorting the bunny. This one is also named skew in by some people in computer graphics. It's also called and actually in some 3D packages, for example in 3 Studio Max, there's a modifier that basically applies this transformation and it's called skew. And there's also another name called transvection. I think that is more like in the math area. At least as far as I know, and I have a lot of years in this industry, nobody in computer graphics calls like that, calls transvection. But in some books you can see that name. Oh, transvection, transformation. So yeah, don't be worried about that. Okay, so do you notice something different from this transformation in comparison with scale, reflection, and rotation? Can you notice something? So you can answer on the chat right now. Think about it. What is changing? By the way, are you hearing me? Can you hear me? Okay, good. Okay. The axis is tilted. Yes, thank you, Kai. Yes. So basically, this transformation basically is not keeping the basis vectors orthogonality, right? So this is a major difference between this transformation with respect to rotation or scaling, right? So if you scale or rotate or reflect, right? Basically, your basis vectors are always orthogonal, right? So this is the difference, right? In this case, the basis vectors are not orthogonal anymore. However, this transformation is also linear, right? So in the end, it can be confusing. It's like, okay, yeah, we understand these are linear transformations, but why they are linear? And what is, in the end, what is the definition of a linear transformation? And why do we need a different type of transformations? In this case, affine transformation. That is basically the topic of today, right? So why we need that? So let's see a geometrical interpretation of that. So for that, I will switch my screen. I will stop sharing. And now you need to see, you must see my, like my camera, right? In Zoom, and you must see like the same dragon will welcome, right? Let me just get something very quickly because I need to get the chat. Sorry, I need to get, oh yeah, actually the chat is there. Someone says backwards, mirrored. Okay, I think at this moment right now, I cannot solve that. So basically you're seeing the word welcome is basically mirrored. Okay, don't worry. So let's do something. Can you see me now? Can you see my face? Great. So what we will do is basically, I want to make like an exercise in which I will show you I will ask you to imagine some transformations and we will try to identify just by seeing how this transformation works, if those transformations are linear or not, right? So again, you will be able to answer in the chat. So please, with the power of your imagination, imagine that we have a bunny here, okay? So think about it. And we have a bunny, okay? So we have this bunny, and this bunny has a coordinate frame, right? It's like this, and is rotating, right? So what do you think about this transformation? This is linear or not? Yeah, your imagination is amazing. Yeah, you have a powerful imagination, very powerful. What do you think? So what is this transformation? What's the name of this transformation? Okay, linear. It's rotating, yes. Linear, yeah. Everybody is agreeing that it's linear. Good. What about this transformation? What do you think? Uniform scale, it's linear. Good. Good. Pay attention to something very important. Imagine that, like here, imagine that this bunny there's a point on the base of the bunny, right? That is basically touching the 0, 0 from this coordinate frame, right? This is a 3D world, 3D Euclidean world. And there's at least one point on the bunny that is basically touching the 0, 0 vector, right? So please see that, try to imagine that point. Okay. So what about this one? What do you think? LSD, nonlinear, nonlinear. Yeah, everybody kind of, yeah, exactly. It's using, it's like it's using a wave, right? Periodic, yeah, good. So I think everybody's agreeing that it's not linear. The thing is, why do you think it's not linear? What do you think? It seems not linear, but why? There's no fixed points. Good. That is one good option. It looks weird. Okay, so if everything looks weird, it maybe is not linear. Wave. Someone is saying not all points move the same direction at given time. And okay. And Raunak is like giving literally the formal definition of nonlinearity, which is very, very nice. And someone is now saying also the origin isn't fixed. Yes, so we are kind of getting there, right? So basically, again, if you imagine that there is a point that is on the base of the bunny, right, and is touching the 0 vector or the 0, 0 of this coordinate frame, now that point on the 0 vector is basically moving up and down, right? So the origin is not fixed. And something that we also can see is that what in the original 3D model were parallel lines or even straight lines, they're not straight anymore, right? So that is also an important geometric interpretation of something that is a transformation that is basically nonlinear. So a linear transformation needs to keep straight lines as straight lines, okay? What about this one? Straight lines are straight lines, and parallel lines are still parallel lines. Okay, so someone is saying linear translation. Okay. Nope. Someone is saying nope. Yeah, so this one is kind of confusing, right? Because everybody was agreeing on the rest, but now some people is saying that is a trap, right? That is not linear. Somebody is saying that is linear. So let's think about it. Okay, so let's get rid of these things and let's come back to our presentation. So I will share my screen again. And it's this one here. Okay. And let me come back to my presentation. And I need to get the chat again. Imagination is gone. Don't worry. We will have similar stuff in future lectures. Okay. So now let's try to let's see the formal definition of what a linear transformation is. Okay. Can you see my screen again? Can you see formal definition? Okay, great. So this is basically the formal definition. A transformation is linear if it complies with the following requirements. And this basically it says that it needs to preserve the basic operations of addition and multiplication by scalars. Okay. So if we add two vectors and then perform the transformation, we must get the same result as if we're performing the transformation individually to each vector and then add the transform vectors, right? Also, if we scale a vector and transform it, we should get the same result by first transforming the vector and then scale it. This is also this also implies that any linear transformation applied to the zero vector must return zero. This is what we were talking about, that if the linear transformation is basically moving the origin, if the origin is not fixed, it means that it's not linear, right? This is super important, right? So from here, we can conclude that translation is not a linear transformation, and it's because it basically translates the origin, right? So a linear transformation cannot contain translation, okay? However, we need to translate objects in computer graphics, right? And we need to move, rotate, and things around, right? And we also need to distinguish between transforming vectors and transforming points. So we already talked a little bit about that. We already talked about a little bit about the difference, the conceptual difference between points and vectors, that we are basically constructed by the same elements, but they are different things, right? So we need something more powerful. We need something that could be a nice, elegant, and compact version of these transformation matrices that could allow us to actually perform translations, and we could also work with vectors or points, right? So let's take a quick break and let's see if someone has, let me just take this screen. Oh, give me a second, I need the participant screen, and it's not there. Yes, it's here. Okay, so if you have a question, please raise your hand. If everything is clear, I can continue. So nobody is raising hands? Nobody? 3, 2, 1. Great. Okay. So let's keep going. So again, let's talk about a little bit of the difference between points and vectors, right? So points represent a position in space, right? And they are constructed by elements. In this case, it's 2D. They are basically constructed by X and Y. If it's 3D, X, Y, and Z. Good. So conceptually, it makes sense to rotate points, right? That is perfectly fine. Rotate a point, it makes sense. If I take a 3D model that is basically created by a lot of vertices, a lot of points, and I want to rotate the model, what I'm basically doing is rotating all its vertices or all its points individually, right? And in the end, I have the entire rotation for the entire model. It also makes sense to scale points, right? Obviously makes sense. And it also makes sense to translate points. Now let's talk about vectors. So vectors, we said that although they are constructed by the same elements, right? They are represented by the same data, X, Y in the case of 2D, or X, Y, and Z in the case of 3D. They represent a different thing, right? So again, a position in space has a associated vector, right? But the vector, what is indicating is motion or direction or displacement, okay? So in terms of data, all vectors start in the 0, 0, 0 of the world, right? You agree? However, conceptually speaking, because they are not expressing a position, but they are expressing a direction, you can see vectors drawn in different places. So they can be anywhere. So if you open a math book or you can see a presentation regarding computer graphics, sometimes you can see in a Euclidean space, you can see vectors drawn in a different position that is not exactly in the 0, 0, 0, right? Because, yeah, conceptually they represent the direction, right? They have a magnitude and direction. So again, conceptually they can be anywhere, right? So let's take a look at this example, right? One of the most important vectors in computer graphics is the normals of a surface. So as we said already, the normals represent a vector whose direction is basically a orthogonal direction to the surface, okay? So for every triangle or every vertex in a 3D model, we have this vector called normal that is basically saying what is the orthogonal direction of the surface, right? And so if we get vectors and we translate a vector, the problem is because vectors are again represented by exactly the same data, X, Y, and Z, in this case xy. If we translate a vector, we are basically modifying its direction, and we even modifying its magnitude, right? So we should not translate vectors. So again, using the example of the normals, right? If we have the bunny and we somehow apply a transformation to the bunny, and we apply to everything, we apply the transformation to the points of the bunny, but also to the normals of the bunny, right? With making no difference between points and vectors. We can end up having the vectors just pointing to another place, right? And this is obviously wrong. And some of you could say, oh, but in the end, the mesh is still there. I could recompute the normals. Yeah, but you lost information that you need to recompute again. And remember, this information, the normals, for example, is passing into the vertex shader, and the vertex shader then the following stages. This information is to be interpolated on the fragments, right? So the fragments have an interpolated version from the normals of the vertices of its corresponding triangle, right? And again, those normals should be not distorted, right? They need to keep pointing on the orthogonal direction from the surface, because they're super important in terms of what you will see then with your third assignment, actually with your third code assignment, that when we actually compute on the fragment shader, compute the final color of something, and we compute that, like the specular level, for example, we need the normal to make a lot of those computations, right? So normals are super important. So what can we do? What can we do to differentiate between points and vectors? So these are points, these are vectors, right? They have no difference in terms of data if you are representing those as x, y, and z. So what we do is we just add another number. We add a little bit more information instead of using the same data. And this new dimension that we are adding, right, is basically like a fourth dimension for both points and vectors. And this is usually called W. Okay, so when someone asks in computer graphics, oh, what is the W of that vector? Yeah, this is the W that they're probably referring to. So points and vectors will have, again, a fourth value called W. And in the case of points, this value will be 1. And in the case of vectors, this value will be 0. So now, if we are trying to apply a transformation, a linear transformation to points and vectors, now we have a problem, because we have a 3x3 matrix with a column vector with 4 elements, and we cannot do this, right? We cannot multiply a 3x3 matrix by a 3-1 matrix, right? So what do you think we need to do? We have the chat. I'm seeing the chat. Make it 4x4. Thanks. Exactly. So we basically add another row and another column to the matrix. So we are augmented the matrix to represent both the translation and the linear transformation. So this is what we need to do. Basically, the part that is the 3x3 matrix will remain being the linear transformation part. So in this section of your matrix, you will have either scale, rotation, shear, or any linear transformation. And somehow in either the column of the vector or the vectors, sorry, the columns or the rows of these new 4x4 matrices, we need to somehow like put the numbers for the translation. Okay, can you guess where can we put it? I mean, seeing these matrices like this and knowing that the points will have a W value of 1 and vectors will have W value of 1, can you tell me if the translation values are going to be in either in the columns or the rows? What do you think? Columns or rows? So someone is saying rows. Okay, we have only one answer. What do you think? Rows or columns? And again, just to not confuse you with the rotation and cosine, whatever, imagine that this is just an identity matrix. So this is just the linear transformation part, and again, this is what we are adding, right? We are augmenting with 4x4. Rightmost column, someone is saying column because it should apply only to the W dimension. Yes, Michael, thank you so much. And Nam is also saying column. Yes, exactly. So yes, we need to add them on the column, right? So basically what we do, this different type of matrix, right? This augmented matrix. In the end, we have the X, Y, and Z values for the translation in its last column, fourth last column. And we will just put zeros on the top, on the bottom, and then a 1 here, right? So this is what we call affine transformation matrices, right? So the linear transformation matrices is basically this 3 by 3 that is inside. But when you take a 3 by 3 transformation matrix and you basically just like increase it by to make it like 4 by 4, this is what we get, right? And these are called affine transformation matrices. And this is very nice because again, because we have a different value on the W component for points and vectors, this is what we get. In the case of points, if you multiply this 4 by 4 times this vector right here, well, this point right here, what you get is basically the transform version of this point, the linear transform version of this point, plus your values for translation, right? And because you have a 0 in the case of vectors, basically your translation is mathematically discarded and you only get the transform version, okay? So everyone is good with this? Good. So this is why, for example, in the vertex shader, this is why you have, when you're dealing with positions, for example, this is why you have a vec 4. And this is why you have, in this case, for example, this is new position, and then you have a number 1 at the end, right? Someone was asking me, or was asking on Piazza, I don't remember, that it was confusing, like why we are not using a vec 3 if it's just a position and it's X, Y, Z? Why we have a number 1 there? And someone was actually confused and asking if this number 1 was the alpha value, right? So if we are talking about colors, we also have 4 values. And remember, in terms of color, we have RGB, red, green, and blue. And the 4th column represents the alpha value, right? But this is not the alpha value. This is the W value that is either 0 or 1, okay? So if you were, for example, dealing with normals, if you were manipulating normals, what is the number that you should put here? 0. Yes, of course, because the normal is a vector, right? It doesn't represent a position, it represents a vector. This is super important. Please remind that. And this leads to many errors or to many bugs when you're basically coding. If you are not completely sure, or you're not aware of what type of entity are you working with, right? If you're working with points, or what you are basically taking represent a point or represent a direction, right? And yeah, you can make those mistakes, because the thing is not always normals, right? So imagine, for example, in animation, it's very common to make, for example, make an object following a path, right? And sometimes we use the information from that path to compute other things. And actually, we will actually do that for this, no, for the third assignment, for the extra points for the third assignment. So basically, we will have like a sphere. It'll basically like roll in a surface, right? So for example, in that case, you need the tangent of the curve that basically the object is following. So again, imagine that I don't know, imagine my mouse is an object that is basically traveling along a path, right? So the path has a tangent, right? A tangent direction, and you can use that tangent direction to compute a rotation axis, for example, if this is a ball that is basically rotating, right? But again, if you apply transformations to everything, right? And you are applying transformations to the objects that are on the scene, but also to all your information that is contained there, including the tangents of, in this case, for example, the tangents of the curve, and you're adding 1 to everything, right? Now your tangents will be weird. And the thing is, in computer graphics, specifically in real-time rendering, we already have the problem of not having debug tools for many things, right? So it's very, very, very hard to debug a vertex shader or a fragment shader. You are probably already suffering about that. So yeah, making these mistakes. The problem is that, like, yeah, they're very, very hard to to find sometimes. Okay. And in terms of matrices, this is why you also create 4x4 matrices, right? So in the case of, and this will be related, for example, with your second coding assignment that is actually very close. It will be released very close, very soon. And this is an example, for example, on how you create a 4x4 matrix from 3.js to perform any specific transformation, right, in 3.js. So you create a variable, and basically this is a 4x4, right? And for example, here, just by seeing these numbers, can you tell me what is this matrix, this transformation matrix is doing? Can you tell me just by seeing the numbers? Is what? Is rotating? Is what? Scaling? Scale? Yes. Yes. Now, thank you. Scale and translate. Yes. Scale plus translate. Because these values here are basically representing the translation, right? So if you don't have any translation, this should be 0, 0, 0, and 1, right? So yeah, this is scaling plus translation. Okay, so now let's take a break. And I'm very happy because we basically finished what I have prepared. And but yeah, I don't know, maybe you have questions. Let's see. So if you have questions, please raise your hand and I can unmute you. Yes, okay.
Hey,
Hello.
hi. I just wanted to know, is it maybe next in the next lecture or something, that how do you calculate the translation values in the 4x4 matrix?
Okay, good. Okay, what do you mean by like? Yeah.
So in the transformation
Yes.
matrix, we have the bx, by, bz
Yeah.
values. How do you calculate those? Like the 3x3, I get that that's the transformation matrix. It depends on what transformation we want to do.
Well,
But then the
yeah. Okay. That is probably the most straightforward part of the matrix, because those are literally your scalar values for the basis vectors, right? Your x, y, z coordinates. So if you have, let's imagine that you want to rotate the bunny 45 degrees in I don't know, z axis, right? So you create the 3x3 rotation on z axis transformation matrix, right? And you put that on the 3x3 section of your affine transformation matrix. And let's imagine that you, besides rotating your bunny, you also want to move the bunny 5 units in x and 3 units in y and 1 unit in z. You just literally write 3, 2, 1 on the
okay,
last column vector. Yeah,
okay, okay, thanks.
you're welcome. Okay, so now, yes.
Hey, what does the transformation matrix look like for the sinusoid example that you applied on your bunny?
I good question. Yeah, the thing is that one is animating. It's an animation. So let me just remember, because I don't have it right here. I made that animation a couple of weeks ago. Give me a second. I think what I apply. I'm not sure. Let me just return to. Give me a second. Give me a second. I think I was modifying only the set values. So I am using a sinusoidal wave. Yeah. So what I'm modifying, yeah, basically I'm modifying in time t. I am probably taking the sine of t. So t is time, right? So I have an animation, right? So let's say
Right.
that the animation is going from 0 to 100. So basically the formula is probably sine of t, and then I multiply everything by a certain number to get the wave length, right? To control the animation, like going up and down, how much I want it to be up and down, right? Yeah.
I see.
Yeah.
So if you think about, um, I guess there's no explicit translation involved in that example. So there's no rightmost column values.
Um, mm, no, exactly.
Okay.
Yeah, yeah,
Okay.
yeah. I mean, it is implicit, right? Because in the end, I was literally no, yeah, no, sorry. It is because that like sine of t times whatever amplitude I wanted, that is actually on the fourth column because I was
Oh, it is.
yeah, it is because I was translating the points, right? So I applied a wave into the set value of the last of the fourth column, right? I am moving
Right.
I am moving them up and down. And also,
Oh, okay. So your sine function has both z value and the time in it.
yes,
Okay.
and also the wave is not if you just use a single wave, right? Everything will be just like the entire bunny will just like move up and down the entire bunny. But here you see like a deformation, right? Like the bunny is deformed. So the the number that you are using inside the sine function, in this case t, you must add something to that, and basically you add your x value, in this case the x value for the positions, right? So basically different for all the points of the bunny, right?
Mm-hmm.
If they have a different position in x, their sign will be different, right? Because you're adding something to t. So that's why
Right.
some parts of the bunny are basically on the up part of the wave, some parts of the bunny are on the bottom part of the wave, because you're using their x value to modify your equation, right?
Right. Yeah. Well, not to follow the rabbit down the hole. Uh, so in animation, I guess there's the state update to the vertices, but you're obviously doing this with respect to the bunny's state at time zero. So that's fixed, and
Mm-hmm.
your sine function is only deforming the bunny's original state rather than updating the vertex at each time step.
Yes.
Okay,
Yeah.
thanks.
Okay, good. Anyone else? Raise your hands if you have questions. Okay. Gloria, you have questions. Oh, sorry. Yes, Gloria.
Oh, sorry, I was muted. Can we go back to the
Sorry,
slides
sorry.
with the linear
I was not
transformation?
sorry. We were not hearing you because you were muted. So yeah, can you
Yeah.
repeat?
Can we go back to look at the slides where the linear transformation is defined?
Yes, of course. Here.
Yeah, I just thought we went through a bit fast, so I wanted to get another look at them. Thank you.
Okay, I think we are good. So let me just quickly go to the end of the presentation. Wow, so we are actually finishing very early. Okay, so give me a second. Okay, matrix. Okay, so the next lecture we will talk. Oh, this is actually incorrect. It's not affine transformation. We will talk about homogeneous coordinates. I would love to actually start the topic right now, but the thing is we still have time, but we have 7 minutes. It's yeah, I think talking about that in 7 minutes I will just confuse you probably. So check Piazza and remember that you have optional readings, right? In this case, if you read the chapter 9.4 from this book, I think this is the second book that we have on our list, and that will be very helpful for you. But yeah, the thing is, this I mean I will talk a little bit about homogeneous coordinates. The thing is, these coordinates that we are using here, these coordinates that they have now, they have this w value, right? They are actually now coordinates in a space of 4 dimensions. So it's very, very interesting, right? So it's not just like a trick that we are using. Oh, let's just add a 1 because it sounds or it seems hacky, right? It's like yeah, just in this way we can use 4x4 matrices and it will be more convenient. Just let's add a 1 and a 0 and that's it. But the thing is, mathematically speaking, this is really interesting because they are literally objects in 4 dimensions and they're living in a space in which remember that we were talking about when we were talking about the coordinates on a coordinate frame. Something that is super important is that we said that if the coordinates of a point P with respect with a coordinate frame are defined, which means that the point P is actually inside the space of this coordinate frame, right? Or I can say differently, if I say it, if the transformation matrix of that coordinate frame is not collapsed, or if the determinant is not 0, right? So if the coordinates are defined, it means that that point has unique coordinates in that space, right? That is super important. But the thing is, this homogeneous coordinates thing, they don't follow that. You will see on next lecture that in this type of space, the coordinates in the Euclidean space of homogeneous coordinates are not unique anymore, right? So yeah, that is yeah, something that I can tell you. But yeah, I think we can finish for today. We are finishing basically 5 minutes before. So please tell me, do you have any other questions before we finish? Either on chat. Okay, Ashley, perfect. So let me unmute. Yes, Ashley. No, wait, give me a second. Yeah, now we can hear you. Yeah.
Oh, hi. Sorry, I know you went over this already, but I was wondering if you could quickly just explain again the reason why we shouldn't translate the vectors. Like, I know what we can do to
Sure. Let me go back.
like the
Yeah, that's we are here, right? I don't. I can repeat whatever
Thank you.
topic. Don't worry. Okay, so this is the thing, right? So
Yeah.
vectors. Let me go back. So remember, vectors they represent a direction, right? And conceptually, sometimes we draw vectors in different parts of the space. But mathematically speaking, or at least, or like with the data you have, a vector, because it's only x, y, z values or x, y values, its origin is always 0, 0, right? So it doesn't matter if you draw it here, right? If it's 7, 4, it means that this vector is not actually here. It is actually, it begins in the 0, 0, right? So if you take a vector like this one, 7, 4, and then you apply a transformation to this vector, it's like you're not applying the transformation to the entire vector, but only to the tip of the vector. Because the only information you have from that vector is the coordinates of the tip. You agree?
Yeah.
In terms of data, the data you have, I mean, if we had a different type of data, maybe in a different universe or in a different time, maybe people could say, oh, no, you need to represent vectors with 2 positions. Its position of the origin and its position of the tip, right? Because in the end, a vector has intrinsically, a vector has 2 positions intrinsically, right? It has its origin and its tip. But it turns out that we decided, as humans, that we will represent vectors only with the coordinates of the tip. So if you apply a transformation, you are applying a transformation to the tip of the vector. So if you move the tip of the vector, and you're obviously not moving its origin, now the vector is different, right? The direction that vector represents, and even the magnitude that is representing, it's maybe totally different. So if we go back to the example of the normals, here I'm drawing the normals in different positions in space, right? Because I'm basically putting normals in different positions on the surface. But again, mathematically speaking, or in terms of data, each of these vectors, all these vectors are all coming out from the 0, 0, 0. Right?
Right.
So if I apply a translation to all my data, the points or the vertices of this bunny, and also to the normals of this bunny, I can end up doing this, right? Moving only the tip of the normals, and basically I could end up having. I mean, this is an exaggeration, obviously, but yeah, I might apply some translation to my bunny, and I could modify the tip of the vectors of my normals. So now the normals are basically pointing to a different place, right? So
Right. So it's not applying the translation to the origin, like the origin is staying the same.
yes, because
Okay.
and the reason is because you don't have data from the origin, right? We only use the three numbers to represent vectors, and those numbers are just the tip of the vector. So you just move the tip of the vector and you scale or modify its direction, right?
Right. That makes
Yeah,
sense. Thank you so much.
good, great. Anyone else? Any other question? Okay, and let me see the chat because I'm only seeing. Thanks. Okay, perfect. Thank you so much, people. Last thing I wanted to tell you just is like I'm also trying to see how many people is on each lecture. So we have sometimes we have 60 people, sometimes we have 70, sometimes 90 something, and but I'm also checking how many people is kind of seeing the videos. Maybe I'm wrong, but I think some numbers are not matching. So I think some of the lectures, maybe some people are haven't seen some of the lectures either because they couldn't attend the synchronous version or they haven't seen the asynchronous version, right? So if again maybe I'm wrong and everybody is already attended everything, but if you by for some reason you haven't attended any of the lectures or you haven't seen any of the videos, just I mean because we having this online course, of course you can have time later to check that, but just don't let videos without watching, right? Because I don't want people to like I don't know one day before the the midterm have oh my god I haven't attended 4 or 5 lectures and I need to see the videos again because those are long videos, 1 hour each video, right? So yeah, again maybe I'm wrong and maybe everybody's actually seeing everything, but if you don't or if you know someone that is not seeing or attending the lectures, please tell them that only by seeing the PDFs maybe you don't have enough information to yeah. So thank you so much. Bye and see you on Monday.